Okay, hello everyone. Welcome to today's webinar, hosted by the Hong Kong Poly BEE and the SIB student chapter. So today's we are so pleasure to invite Dr. Xu to have a webinar for us. Dr. Xu is a fire engineer at the Witteveen+Bos, a consulting company in the Netherlands. He received his PhD from the Eindhoven University of Technology. And today his lecture is about the fire dynamic simulations in structure stability prediction and fire safety assessment. Okay, let's thanks Dr. Xu again, and Dr. Xu, you can start.
Oh, thanks, Yufei, for your introduction. And yeah, before I start, I also would like to have a brief introduction of myself. My name is Qingfeng, and currently I'm a fire safety engineer in a Dutch consultancy, which is named Witteveen+Bos. And yeah, wait a minute, I will use my pointer. So last month, I just successfully defended my thesis. So I'm so glad that I can officially call myself a doctor. And today's presentation is about partly about my PhD project, and also I will explain some ongoing projects here in the Netherlands. Before I start, so feel free to stop me if you have any questions or comments or remarks regarding the content. And I will start with a problem description. So the fire is a very complex problem because it can occur at any places, like for example, the tall buildings, shopping mall, airplane, tunnel, vehicle, ships. Because we cannot predict where and when the fire will occur. So we would, as a fire engineer, how can we minimize the damage of the fire accident? That's a main problem for us. So from the engineering perspective, we need to do the proper fire safety design to make sure the structure have enough fire resistance capability. But when we're talking about the interaction between fire and structure, normally we only consider the one way, which is a fire influence on the structures. But if we check the video here, when the firefighters break the window, or the window can be broken by the fire, we can find the structure failure also will gradually affect the fire development inside the compartment. So today's presentation is about two parts. The first part is about fire resistance capability of structures, which is about building with connections and insulation systems. So this part is about my PhD project. The second part is about fire safety design and the risk analysis in projects, which is some ongoing projects I'm doing here in the Netherlands. So the standard panel system, actually, as I showed on the right-hand side, you can find it's a lightweighted structures which consist of two thin plates with an insulation layer. They are widely used in the buildings as an external wall, which we call it facade, because it's lightweighted and easy to construct it, and also they have relatively good insulation properties. But when it is exposed to fire, and if we do not carefully take into account the fire resistance of these structures, we may have some catastrophic consequences. For example, the Grenfell Tower occurred in 2017. We can find this they use a lot of central panel on the facade. Yes, sure. Any questions? Oh, okay. I'll just continue. So you can see this central panel facade, which is supposed to be fire resistance, but during fire, because of inappropriate design, they were burning during the fire, and as a consequence, a lot of people lost their lives. So, yeah, the most trustworthy or the most reliable way to check the fire resistance of central panel system is by doing the full-scale test. So, for example, we can put the central panel on top of the furnace, where we can measure the temperature and the deformation of center panel system. But doing such a full-scale fire resistant test for center panel are very expensive. For this one single experiment, it may cost more than 10,000 euro, which is literally we are burning the money in the furnace. So the best alternative as a full-scale fire-resistant test is by doing the simulations, where we can simulate the fire by the computational fluid dynamics model, and also we can simulate the structural deformation by a finite element method. The reason why we cannot put them together, but to do it sequentially, is because the governing equations for these two physics problems are different. So we first need to run the fire dynamic model, and we import the data to the finite element domain. So but if we look into the center panel system, you will be surprised how many details are there. For example, they have so many connections which connect to the steel frame with the column using the bolted connection. They also fix the center panel with a steel section using the screw connections. They also have the insulation layer, which is a very complex chemical material. It's a very complex material, and when this kind of material is fire exposed, it may release a lot of gas, and it makes us very difficult to predict the temperature distribution inside the material. There also have some other details, for example, the tongue and groove, glue layer in between. There are so many details, so we cannot properly model these details. So we have to use a full-scale experiment as a verification to check if our models can more or less accurately predict the whole system. So the existing challenges I have listed here is just something I mentioned before. And the aim of my PhD project was to develop a numerical model that accounts for the aspects mentioned above, and finally improve the accuracy of the failure prediction for center panel system. So I want to use the numerical model to predict the failure of the center panel system during fire. Let's first start with the first two topics of my PhD about connections. So for the full-scale center panel under fire, of course, if we want to predict the behavior, of course, we can establish a finite element model, and using more elements or smaller element size, it can give us better prediction for such a system. However, if we look into it, there are so many detailed connections, such as bolted connections at here. And if we zoom in, you will be surprised how many details are there for the bolt. For example, it has a bolted head, bolted nut, and they have so many threads. If we want to model such a small detailed model in the large system, the computational cost will be increased dramatically. Therefore, I propose a method which we keep the plate over here, and we would like to use element as a representative for the bolt listed here. So the behavior of the spring element will be more or less equivalent as the bolted connection here. I call this method as a two-scale method. I want to make sure the behavior of the two-scale method was more or less the same as a detailed system model listed here. As we have some Eurocode, they put some failure modes for the bolted connections: bearing, shear, tension, bunching, combined bear and shear failure mode, and they also have next section failure mode. So by verifying this detailed system model, these failure modes by the two-scale model and the detailed system model, they showed more or less a similar behavior under different loading condition. So in this way, I more or less verified the two-scale method with the detailed system model. Excuse me, any questions so far? Okay, I'll continue. And the second topic of my PhD is that I extended the two-scale method for the screw connections. So because for the bolted connection, we have more or less asymmetric contact region over here. But for the screw connections, they have some different contact region. For example, for the screw head, it will contact with the center panel. The contact area is this much, but for the tip of the screw connection, it has a relatively smaller contact area. Therefore, I updated my two-scale method for the screw connections over here. But the idea is more or less the same as a bolted connection. We still have the spring element as a representative for the screw connections, and where we can obtain the temperature and the displacement under conditions to the small scale model. And then we can calculate the response based on the structural analysis for such small scale model, and we will update the stiffness of the spring element. So by using this loop, we can predict the failure of the screw connection by not modeling the detailed screw in this big system. Then I incorporate this two-scale model in a two-way coupled fire structural simulation. So for the coupled fire structural simulation, we first started with this fire dynamic simulation, where we can obtain the temperature field around the center panel system. And this thermal data can be imported in the finite element domain to do the heat transfer analysis. So we can obtain the temperature distribution over the thickness direction. And this this temperature distribution can be imported in the structural analysis model to do in this way we can check the deformation of the center panel. And here we can use our two-scale method. You can see the small spring here, spring element here. And by using two-scale method, we can predict whether the screw connection failed or not within this loop. If the screw connection does not fail, we will simply calculate and update the spring stiffness based on the calculation. But if the screw connection failed, we will remove the plate in the fire dynamic simulation. So as a consequence, there will be some oxygen, and the fire development will be changed. So this is a so-called two-way coupled fire structural simulation. So to put them together, in the first two topics, I developed a two-scale method for the bolted and the screw connections, and I successfully verified my two-scale method with a detailed system model and existing Eurocode. And also the two-scale method has been successfully included in a two-way coupled fire structural simulation. So let's move to the third topic of my PhD, which is about insulation layer. When the center panel is exposed to fire, it will not burning like a wood. The fire will introduce a lot of heat flux on top of the center panel, and as a consequence, this insulation layer will gradually decompose. We can divide the insulation, a fire-exposed insulation, into three regions. So the dark side, we call it pyrolyzed material, which means this part within this part, the whole material will be charred. And we also have the virgin material, which is the chemical reaction is not happened there yet. But the most interesting part is a decomposition region, where the chemical, or we call it decomposition, or the pyrolysis behavior is happen there, which may release or absorb a lot of heat. Only when we consider this behavior can we more accurately predict the temperature distribution over the thickness for the insulation layer. So what I did here is I tried to update the Gaussian equation of heat transfer. So we take into account the pyrolysis reaction and the mass flux, as I showed the last two parts for the heat transfer Gaussian equations, and I compare the developed pyrolysis model with previous experiments. So this is a composite material, and one side, the end of the cylinder, is exposed to constant heat flux, and we can measure the temperature inside the cylinder at different locations. So with this pyrolysis model, I can more or less predict the temperature development inside the cylinder. So as you can see here, we have an experiment show as different dot. We also have the numerical simulation results shown as a line. So they are more or less have the good agreement. After this verification, I also incorporate the pyrolysis model in a two-way coupled fire structural simulations. So similar as what we did for the two-scale model. First, we have a center panel here. We start with fire dynamic simulation, and we do the heat transfer analysis, where we can incorporate the pyrolysis model, and we can predict the degradation inside the insulation layer. And then we run another structural response analysis to check the failure of the center panel. If it's a failed, the fire simulations will be changed, and so on. The structure model also will be changed. So I also compared the model with and without pyrolysis. Actually, quite surprisingly, you can find for the model without pyrolysis model actually shows the higher temperature compared to the model with pyrolysis. This is because the pyrolysis reaction actually it absorbs a lot of heat, so it may reduce the fire risks than what we expected. So to put it all together, in the third part of my PhD, I developed a pyrolysis model, and I successfully validated it with previous experiment, and the results shows an accurate degradation prediction for the insulation core. And the pyrolysis model is also incorporated in the fire structure coupled simulations. Now we can move to the last part of my PhD, which was about the experimental validation for the rushed details inside the center panel systems. So the first experiment I did was about the center panel facade test. As you can see here, it's a very big center panel systems. It's around 5 meters high and 4 meters wide. And when it's fire exposed, the center panel will behave like this. So it will bending toward the fire. And And we also have some screw fixing the center panel system over there. So I established a finite element model, and of course you can see some displacement and thermal displacement sensors and the thermocouples on top of the center panel. So I established the finite element model, and I measured the deformation in the center, at the center of the center panel, and I compared it with the experimental results. As you can see here, at the end of the fire, actually it shows more or less same results for the central deformation. However, at the beginning of the fire, it has a very big gap between the simulation and the test. So I did a lot of parameter study, but I think it must have something to do with the dynamic behavior at the beginning of the fire. Because if we compare the initial stiffness of the center panel, actually the simulation and the test they showed more or less closed behavior. But at a certain moment, the test is dropping. The displacement, central displacement is dropping in the test. So we did a lot of parameter study to check what happened there. We checked we used the fire dynamic model instead of fire curve. We checked the thermal expansion coefficient. We also tried to change the modeling method for time and groove connections. I also vary the screw connections stiffness, but they were not the case for such a big gap. And finally, when I changed the modeling method for the glue layer, because the assumption for the center panel is always the steel surface will be closely attached to the insulation layer. But when I try to lose the connection between the steel surface and the insulation layer, actually I found the difference has been decreased a lot without influencing the final results in our model. So I believe the initial difference between the numerical model and the test was due to the detachment for the glue layer, because during the experiment we also found a lot of buckling on the fire exposed side of center panel. And the second test I did was called the stud bolt test, which we fixed the center panel inside the furnace, as you can see here. And the intention for this test was to test the fire resistance of the stud bolt test. And but the stud bolt did not fail during the fire, but the screw connections failed during the test. So the idea is I forgot to mention, we also have like a 1 kilonewton dead load at the bottom of the center panel, and the screw connection failed during the fire test. And we would like to use the two-scale method to check or to predict the failure of screw connections during the fire. So I established a two-scale model. You can see here is our spring element, and here is our small-scale screw connections. And I run the simulation at different temperature. It tells us with that 1 kilonewton external load, actually the failure temperature will be 800 Celsius degree. Of course, if you have a like 2 kilonewton external load, the failure temperature will be 700 Celsius degree, and so on. And we said that the 800 Celsius degree prediction, I checked the heat transfer analysis in my model. It tells me like for the spring element here, it will reach 800 Celsius degree at around 3,150 seconds. So then I compare this failure time prediction with the test. Actually, the error was only 2 minutes, which means I successfully verified my two-scale method with the experiment. So, but to sum it up, in the last part of my PhD, I successfully verified the numerical simulation with two full-scale fire-resistant tests. And I found the glue layer decomposition related dynamics and instability at the beginning of a fire. Actually, it matters a lot for the deformation prediction. And also, I have used the two-scale method to successfully predict the screw connection failure. And as a conclusion, so the two-scale method. So for my PhD project, I have developed the two-scale method for the bolted and the screw connections, and I verified this two-scale method with a detailed system model, error codes, and available experimental results. For the insulation layer, I developed the paralysis model and implement the paralysis model in the fire structural couple simulations. And also, I used the two full-scale center panel tests to verify the manual model. But most important conclusions for this PhD project is it presents innovative simulation techniques along with open source codes and models, which can be used in both scientific research and engineering practice. So if you are interested in my PhD work, you can simply find my thesis online. And at the bottom of my thesis, all the codes, models I used is all public. And also the related findings supports the further development of fire safety regulations and the future building design. So that's part of my that's about my PhD. Any questions so far? If not, then I will just move to the second part of this presentation, which is about ongoing projects I have been doing here in Witteveen+Bos. So what we are doing here is it's a very big project in Belgium. It's a city called Antwerp. So as you can see here, there's the northern part is the Netherlands, and this part is Belgium. And then we would like to build a lot of roads or infrastructures to connect the Belgium together with the Netherlands. So this the colored lines are the constructions we have been doing now. There are a lot of roads, tunnels, building there. And what I've been doing is I am doing the fire safe design for these infrastructures. For example, they have different assumptions. There will be a lot of dangerous goods or trucks transferring every day from Antwerp port to the Central Europe. And we will assume, okay, if the fire accident happens there, and there's a retaining wall here, should we protect this retaining wall using insulation materials? Of course, we can use some standard fire curves. For example, we can just directly apply these fire curves on the retaining wall and to check this behavior. But it's not the most ideal case because in practice, it will not, like such retaining wall, they will not be engulfed by the flame directly because we have some barriers here. And so if we directly apply the fire curves here, it will be some over design. Therefore, I made a CFD model because I want to know what will be the real temperature for these retaining walls. I made a model as here and I put some measurements here. And here's our target, the retaining wall, which consists of a steel sheet pile and also the soil behind this sheet pile. So this is made of steel, and the green part we assume is all soil. And the simulation tells us now. First of all, we get some information from the structural engineers. It tells us for that sheet piles, the failure criteria will be 550 Celsius degree. This was calculated by structural engineers from the stability analysis. And then I look back at my fire dynamic simulation. It tells me the maximum temperature for the retaining wall will be like 535 Celsius degree within 30 minutes, because our target was to make sure the retaining wall will not collapse at the 30 minutes fire. Therefore, we have our results. We made our decision. The protection for the retaining wall is not necessary. That saves us like more than €1 million. And another example is for the, should I call it tunnel? Because it's a quite special structure in Antwerp. For example, it looks like a tunnel, but here we have some open space which connected by beams and columns. And similar as what we did for the retaining wall, we have some fire protection adhere for sure, but the question is, should we protect the beam and the column as well? So to solve this problem, I established a fire dynamic model and checked the temperature over here. It tells us, based on the heat transfer and structural analysis, we will compare these results with the available Eurocode or the failure criteria from the Belgian clients and let them decide if it's because from our calculation, for sure this beam, like one beam, will fail. And then we ask the clients, can you accept the consequences when the one beam failed during fire? If they said yes, then this design will be approved. But if it's no, probably we'll consider to make some fire protections for the beam. So this is how it works in the fire consultancy here in the Netherlands. And of course, we have more projects. For example, we have I did some simulations for the Brussels airport. There will have some terminal extension, and we designed the ventilators on top of the buildings. And we would like to use fire dynamic simulation to check if the ventilators can extract all the smokes when the fire occurs. And that here we had more tunnels in Antwerp, and I checked when the truck fire occurs, will these ventilators have capability to blow all the smoke to blow all the smoke to the front of the traffic, so it will not have any back layering, so people can escape safely. This is the summary for my current consultancy job. So the building, like you can find in Europe, building or structures will not always 100 complying with the regular specifications in standard or codes. And the fire simulation can be a useful tool to solve the practical problems. This is so-called performance-based fire safety design. Then we also found that fire dynamic simulation are more flexible than the standard fire curve, as they account for fire size, location, duration, and field type. This kind of information are not described in the using the standard fire curves. And also the fire simulation capture the combustion physics like oxygen consumption and smoke production. So they can be very useful for designing the fire safety strategy in building and the tunnel ventilation systems. So as I showed the example before. So here I also put a picture of my fire safety team. We are not very big, but you can see we can do a lot of projects for such a big Antwerp projects. I would like to thank all my group members for their support for my work. So that's all the story. Thanks for listening, and hopefully we still have some time